Greetings and welcome to another Eigenverse tutorial. This episode is called Put That in Your Pipeline and Find Your Way Through It, or How I Learned to Stop Worrying and Love the Point Wrangle. This is, I'm not going to lie to you, probably the most advanced tutorial that we have done or even considering doing, because we are going to spend the next hour dealing with very vexing programming language called Vex, which is the built-in programming language in Houdini, the industry standard in VFX tools. And we're going to create a very powerful algorithm that you can use to create assets for projects of any scale, whether it's film, for video games, or for the Sunday papers. Yes, we are going to create a maze generator. But this isn't really about mazes. All right, what this is about identifying a problem, in particular with the scope of your project. Like, you can make one maze by sitting down with a pen and drawing it out, and then you could make it ready for a video game by just throwing together a bunch of walls in Houdini. But could you make a 100 by 100 grid maze? Could you make 100 of them? Eventually, you're going to get to the point where you don't want to do these mazes anymore. You want to get some magic robot that makes your mazes for you. And that's ultimately what we're going to create here. So how do you solve these sorts of problems? You start general, and you drill your way down to be specific. As quickly as possible, really. So let's start general. What is a maze? It's a twisty-turny path that you have to find your way through. In particular, it branches. If you take the wrong path, you're going to spend more time in the maze. So you might be thinking about a maze as making walls, but really the essence of the maze is the path between them, the path that you have to find. This might be counterintuitive because, you're in Houdini, you're probably an artist who thinks about constructing objects rather than constructing the absence of an object. In this case, the absence of whatever the walls are made out of. But the procedural nature of Houdini is perfectly suited for this sort of problem, where we start with something abstract like a path, and then we can turn that into a series of walls with that path very quickly and easily. So how do we carve this path out of these walls? I was thinking about real mazes, like hedge mazes, where they're usually made out of some sort of green foliage, and then you carve some path out of it. So I thought, okay, let's take a big cornfield. Let's put our robot in the cornfield with a lawnmower, a really, really powerful lawnmower, equipped with plasma cutters and powered by kyber crystals. Because I don't know if you've ever tried to take a lawnmower through a cornfield, but it's difficult. But this robot can manage it somehow. And it's going to move around on a grid in this cornfield. Let's say that there's this grid of robot tracking beacons. Maybe they're like glowing stalks of electric cord or something. And so what this robot's going to do is it's going to move from beacon to beacon, carving out linear paths between them on this grid. And that's going to create the path for our maze. And due to the clumsy nature of programming while making art and everything else, this robot isn't going to have much of a hard drive. Instead, we're going to use this hacky technique that I came up with to basically store all the information on each of the beacons. So in order to tell where the robot is, where it's been, where it's going, all the robot needs to do is look at the beacons, which in this case is going to be points on a grid. In Houdini terms, they're going to be points in a mesh stored in a geometry container. So let's take a look at this. We're first going to start off with our grid of points. Here I have it here in a 7x7 grid. The first thing we're going to do to this grid is block off all the points in the perimeter. We're going to mark them with something that says they are not valid points, other than the start point and the end point. This way, our robot can neither enter nor exit the maze, except in the start and end of the maze, which hopefully makes some sense. Next, we're going to mark the start point as our current active grid point, and then we are going to test for nearby valid points. In the start point, there is only one valid point. So on our next step, the robot will move to this valid point, mark that as its current point, and then test all the nearby adjacent points for validity. It's going to continue this process until it reaches a dead end. That is, a point with no adjacent valid points. All the points are either in the perimeter or they have already been used. In this case, our robot is going to turn off its lawnmower, walk back to a previously activated beacon, and set that to be the active point. It's then going to test for valid points and continue this process yet again, carving out a new path until it reaches the endpoint. I have marked this path in a different color, first of all so that you can see the split here, but secondly because this is actually going to be represented in Houdini. Each of these branching paths is going to be what in Houdini is represented as a prim line, and there are going to be as many prim lines as there are branching paths through the maze. So one thing the beacons will have to keep track of to keep telling our robot is which prim line to add each new point to. Now, as you can see, we have reached the endpoint of this hypothetical maze with our hypothetical robot, and now it's time to get real. So let's boot up Houdini and get started. All right, so we got this robot who's going between beacon and beacon in a giant cornfield to carve out a path. So what part of that do we do first? Well, we want the path first, but we need the beacons to make the path. So we make the beacons. Right-click, make a geocontainer, and let's get started. So to make these beacons, we want them in a square grid, so we'll type a grid. And you'd be amazed how many of these crazy advanced looking things start off with adding a grid. But we don't want a checkerboard, we want a go board. We want to focus on just the points. So to delete all the geometry and keep the points, obviously you add an add sup, and you say delete geometry but keep the points. Visualize that, and now we're about ready to get started here. The robot will start around here. Actually, let's say they'll start around here and move over here, and the maze will be in between. So in order to better target the particular points on the grid, let's move it in such a way that we can more easily target it with our math. So first of all, let's make sure the grid is only a 1 by 1 size. Next, for the rows and columns, let's make them 14 by 14. It can be anything as long as it's square for now. Then next, let's add a transform after this and move it 0.5 on the X and 0.5 on the Z. And if we visualize that, now we have a nice grid here that goes from 0 to 1 in both the X direction and the Z direction. And this will be our starting grid, so I'm just going to box this off and call it the grid. So now it's time to get started with our robot. And any agent that performs some sort of action needs to have some sort of prior knowledge to it on which it's going to base that action. So basically we need to declare some variables here and initialize some settings so that our robot knows what it's going to do. And I'm going to do this a very hacky way. Instead of creating some sort of global variable, I'm going to create a variable and then put it on every point in this grid, so that no matter where the robot is, to know everything that it needs to know, it just needs to look at whatever beacon it's on. This will make sense, hopefully. So first of all, I'm going to add a point wrangle. I'd like to say this is going to be the only point wrangle, but you will soon find out that this is going to be one of very many. Because right here we're just going to initialize our first variable, and this is going to be for the random seed. So we're going to type here float at seed modifier equals 0.0 semicolon, and then we're going to say at seed modifier equals CHF seed modifier. So now we hit this little slider thing, and we now have a slider that we can use to change our original seed. This is called the seed modifier because, as you'll see, our seed is actually going to be a little more complicated than this. Next, we're going to add some more variables that are going to help the robot keep track of where it is. So first of all, we're going to mark off the perimeter. We don't want the robot to move into the perimeter unless it is at the start or the end point. This is going to make sure that there's a big wall around the edge of the labyrinth. So drop down a point wrangle. And we're going to set all the points in the perimeter to be in the perimeter group. So if at p.x equals 0, or double bar at p.z equals 0, or at p.x equals 1, or at p.z equals 1, then that means it's in the perimeter. So we are going to say I at group underscore perimeter, set that equal to 1. There's many ways to put something in a group, and for some crazy reason, this is the one that makes the most sense to me. So if it's 0 or 1, put it in the perimeter, else I at group non-perimeter equals 1. And otherwise, this will default to 0. So just to make sure everything's working, you might want to keep checking your geometry spreadsheet to make sure that these groups are created and more or less the right number of things are in the right thing. All right. So the robot can't go on the perimeter. The next thing that it can't do is go to a point that's already been used on its path. So to do that, we'll create a used group. Point wrangle I at group underscore used equals 0. We'll just initialize all of them to be unused. And this is going to become a trend if it hasn't already. Next, we're going to create the current group. Let's first add a point wrangle. I at group underscore current. Set that equal to 0. Now we're going to add another point wrangle. And we're going to make sure that we know what part of the path we're on. We're going to set a prim to use variable. So I at prim to use equals 0. You might notice that this is not a group. What's the difference between a group and a normal integer? Well, you might be thinking of groups in a particular way, and usually it really just has to do with whether or not you feel like it's a group. But a group can be 0 or 1, and an integer can be any number. Technically, there's no difference other than that. So the one other thing our robot really needs to know is whether or not it's on the start or the end. So let's add one more point wrangle. And say I at start equals 0. And I at end equals 0. And next we're going to let every beacon know what the endpoint number actually is, just to make it easier to test for us. So we're going to say I at endpoint number equals 0. All right, so what have we just done? We just laid down a whole bunch of point wrangles and created a whole bunch of variables. And just in case this is the first Houdini tutorial you've ever watched, a point wrangle is something that goes over every point. It is a giant for each loop for each point. So for each point, it's going to add this property here, like right here, we're adding the seed modifier to every point. This is redundant and slow and terrible coding. However, we're not making a video game, and video games and other real-time rendered programs are the only time when it actually matters to be efficient. So this doesn't matter. Do not quote me on that. And just to reiterate, we created a seed modifier. We labeled the perimeter groups. We created the used group. We created the current group. We labeled the prim to use. And we dealt with the start and end. So now we need to start thinking about what the robot's actually going to do. It's going to start from some start point, which we're eventually going to put over here, and then it's going to jump from point to point. Now, in order to make this jump, the robot's going to need to know how far it can jump. So we're going to need to calculate this distance. So we're just going to create another point attribute. Here we're just going to use the attrib create, and let's call this rows in grid. So here we're just going to tell every point how many rows are in the grid. And we can get that number from up here in the original grid SOP. So let's copy the parameter from the rows and paste the relative reference in here. And yeah, I'm not sure where it goes, so we'll just paste it in here for good measure too. So now that we know the rows in grid and we know the size of the grid, namely it's 1 by 1 unit, we can add a point wrangle, of course, and compute the distance from one point to the next. So we're going to create a float attribute, distance between points, and we're going to set that equal to 1.0 over our rows in grid attribute. And then we're going to multiply this by a slightly larger number. So say 1.1, just to make sure, just to account for rounding errors, to make sure we get that extra point. So let's box this. And now, after all that, we are finally ready to drop our robot into the grid. And that's only going to take 4 more point wrangles. So, okay, let's add another point wrangle. And this time we're going to add a polyline. However, remember, this point wrangle is actually going to go through every point. We don't want to add a bajillion polylines to this, so we're actually going to run over detail only once, because we only want to add one polyline. So to create the polyline, we're going to go add prim to the 0th geometry of type polyline. And a polyline is basically a path that connects 2 points. What points is it connecting? Well, none yet. So let's get on that. First of all, let's figure out where we want to put our start. So let's call this add polyline. And then let's make another point wrangle and call it set start. And I'm just going to hard code it so that it's halfway up the middle on the side here. So let's get whatever point is closest to this general area. To do that, we're going to use the near point function. So let's say int local start point equals near point of the 0th geometry. The vector, let's see, what is this? 0.5 on the x, 0 on the y, and 0 on the z. Because I wanted to start from around here. Next, we're going to add this start point to the polyline that we just created in the previous attribute wrangle. You follow? All right, so add vertex. That's how you add a point to a polyline. To the 0th geometry, the 0th prim line, because we only got one. And we're going to add the local start point. Once you add a point to a prim, it's considered a vertex. And at this point, we're going to do this 50,000 times. We only want to do this once. So let's go detail only once. And one more thing we're going to do in here, we're going to set the point groups of this first vertex. So set point group, the 0th geometry. I'm going to set its used group, the local start point, and we're going to set it to 1. And we're going to do the same thing for the current group. So now the start point is used, it is current, and it is added to the prim line. Now we're going to do pretty much the same thing here for the end, so I'm going to copy and paste this. Rename this to set end. And we're going to call this local endpoint. And for this one, we're going to do 0.5 on the X still, but 1.0 on the Z. And we're not going to add it as a vertex to anything, but we are going to set it to the end group. And also, just to make sure, we're going to notify all the points of the endpoint number with another point wrangle. This one will run over points. Int local endpoint equals, we'll just do the same thing we did earlier, near point 0, and where we said the endpoint was it 0.501. And we're going to say I at end, let's say, did I capitalize it? I didn't capitalize it. Okay. I at endpoint number. How did I spell it? All right. I at endpoint number equals whatever this local endpoint is that we found. And let's box this and call it getting started. And there we go. Our grid is ready. And if you check your geometry spreadsheet, you will clearly see that we have a whole bunch of attributes and groups. And now finally, it is time to actually make our robot. And our robot lives inside of a solver node. So let's add a solver. And let's go inside of that, drag down from the previous frame, add a point wrangle, and then add an output. And visualize that. Our robot is actually going to be entirely in one point wrangle. And just to make sure that this will start rendering and everything, let's go up and add a null after the solver and visualize that. So let's go back in here and start typing the brains of the robot. So, whoops, I have a compile error here. Not start point, this is the end point. All right, cool. So let's picture this. We've dropped the robot right here. As you can see, this vertex has already been added to the prim. So the robot is here on the start point. We're going to want it to jump one in, and then we're going to want it to jump to another beacon. And it can go in any which direction. And then whenever it goes to a new point, it's going to check, okay, is it in the perimeter group? If so, check again. Have I already used that point? Okay, then check again. How about this one? Is this fine? Sure. So the robot can then move there. And it's going to keep going until it finds itself in a position where it has no extra movements it can make. In which case, the robot is going to jump back to a point it's already traveled to, and then it's going to try again, adding a new path or a new prim line to the geometry. And it's going to keep doing this until it finds itself right next to the endpoint, which is a special case in which we're going to jump to the endpoint. And then the robot will then just continue on as long as it wants, filling out the rest of the maze. So the first thing we want to do is have some system where we look at the point we're on, and then we look at every point that it could possibly jump to, and then check to see whether or not that point is valid. And we're going to do that by creating a bunch of nested groups until we eventually have a valid destination group, and then we'll jump to that. So let's get started. Despite the fact that this is a point wrangle, we really only want it to activate once, namely for the currently active point. So we have a group for that. It's called the current group. So what we're going to say is if I at group underscore current equals 1. And then we're going to put everything in these curly braces. That way, this code will only execute for the current point. However, before that, maybe we can set a couple more variables. First thing we might want to do is make that proper seed that I was talking about. Let's make a float seed and set that equal to, let's say the point number, let's say plus the seed modifier multiplied by the frame. That way we've got all sorts of variables in here, and it's going to be different pretty much every time it checks. Next, let's just, if we remember, there's a very special case when the robot is making the jump, and that's if the endpoint has been found. So let's just initialize an integer called endpoint found and set that equal to 0. If that changes to 1, in other words, we found the endpoint, then we'll take a different path. So now let's go back into our if block here. If we are on the current group, then let's find all the nearby points. So that's going to be an array of integers, and we're going to call that nearby points. And set that equal to the near points of the 0th geometry around the position marked by the point attribute of the 0th geometry, the attribute called P of this current point. And how far are we going to check? We're going to check the distance between points. Semicolon. So those are going to be all the points that are in range. However, they won't all be valid destinations. So let's initialize a valid points array. Remember that points are just integers. And now we're going to loop through the nearby points and check them. So for each integer nearby point in nearby points, well, since the endpoint is special, let's check for that right now. So if the nearby point is equal to the endpoint number, and it's not equal to the point we're currently on, we're going to have to keep checking for that so that we don't jump to ourselves. Then in that case, we're just going to say that we found the endpoint. Otherwise, if the nearby point is not equal to ourselves, let's make sure that it's not in the perimeter and it's not used. So if nearby point in point group, the 0th geometry used nearby point is equal to 0, so it's not used, and in point group 0th geometry perimeter nearby point is also equal to 0, then in that case, it's probably a valid point. So let's add it to our valid points list that we created up here. Remember? Up here. Okay. So push valid points nearby point. And that's how we add the nearby point to our valid points. And I think that's it for our check. So now let's go down here and start dealing with the logic of what to do now that we found our valid points. All right, so we looked at all the nearby points and we found which ones are valid. Now, we got 3 cases that could happen here. One is if the endpoint is found. And then we're going to do whatever we do when we find the endpoint. The second thing that could happen is if we found some other valid points. So if we didn't find the endpoint, but if the length of the valid points array is greater than 0. And in that case, we're going to do the more general case, where we're going to just jump to some random point. Otherwise, if neither of these happened, then apparently we hit a dead end. So these are going to be the 3 cases that we could have. So let's write the code for each of them. Let's start with the general case. That is to say, we found some valid points, but not the endpoint. So first, let's count how many points we have. Integer valid points number equals the length of the valid points array. So now we're going to do a little trick, a little combo move, if you will, in order to choose a random index from this array. So if you glean anything from this giant tutorial, remember this little combo, because you can actually use this in lots of stuff. So let's say the integer called chosen index equals the floor of the fit of the rand of the seed. And we're going to take it from 0.0 to 1.0, all the way to 0.0 to the valid points number. So what's that? What's the floor of the fit of the rand of the seed? Well, what we're doing is we're taking a random number using the seed, which will be from 0 to 1. Then we're expanding that to go from 0 to the length of the to the valid points number, which is the number of indices we have, the number of valid points we found. Then we're flooring that to make sure we have an integer. You know, we don't want the 2.3rd valid point. We want the second valid point or the third valid point, you know? And this is going to choose a random index from the valid points. So it's going to choose a random point to jump to. So let's say the integer vert to add is equal to valid points array of the chosen index. And then finally, we're going to add that vertex, the 0th geometry. Let's floor the prim to use, and let's add the vert to add. And let's say that this vert that we just added, the vert to add, let's make that our current point for our next loop through all this. So, set point group, 0th geometry, current, and the vert to add, set it to 1. And let's just do the same thing for used. Copy, paste, used. All right. Next, we need to update the last point, which is the point we're currently editing. So again, all of this code is in this one point. We just added this new point. So we're changing that thing's point groups, and then we're changing the old thing's point groups. So you can either wrap your head around that or just copy my code. So I at group used equals 1. So we just used up this point. And then the I at group current equals 0. That old point is no longer current. All right, cool. And that's a general case. Now, if we actually play this, we might be able to see things, do things. Let's see. Oh, look at that. Yep, that's a thing right there. Doesn't look like a maze, though. So we got to work on those other cases. So let's dive back into that solver. I just wanted to show you that something eventually happens in this video. So let's first do the endpoint case because it's pretty much the same thing. You can't see this, but I'm just jumping up and down for joy right now at the fact that I don't have to redo this tutorial again because it works. So, okay, endpoint case. You know the drill here, so I'm just gonna jot this down here. Int vert to add equals floor of the endpoint number. We found the endpoint number, so let's just add that. Now add it to the vertex. Zeroth geometry. Floor of the prim to use. And the vert to add. And then the thing with the groups, set point group, zeroth geometry, current, vert to add, one set. And then do the same thing here for used. And then that's for the new point. So for the old point, I at group used equals 1. And then I at group current equals 1. Or actually equals 0. Why don't I just use a set point group function again? Well, we're changing it up because this is the advanced tutorial. All right, so here's the case if we found the endpoint. Really, this is just to shorten things up and to, make sure that we hit that endpoint. And then here's if the general case. Now, if you see this, let's see what it was actually doing here, just so I can drive this point home. If we advance through here, you can see that even if it finds no place to go, it'll still add something. So all of this also is being only added to one prim. So if you check the prims here, we only have one, the 0th prim. So that's not what we wanted. We wanted it to go until it hits a dead end and then for it to splinter off and make a new path. So let's reset this here. And let's go back into the solver and deal with this dead end case. So first of all, let's just say that this is no longer the current point to get ready for the next loop. I at group current equals 0. Now we're going to add our new prim. So we're going to create a splinter path. Let's call that int local new prim and set that equal to add prim 0, polyline. Now we're doing two things here in this one line here. We are adding a prim, so we're executing this and writing in here that we're adding a prim, and we are then setting that equal to a local variable in this wrangle. So now we're going to get a list of all the points. Here's another one of those things you might want to take away, store in your pocket here. Int all points, make that an array, equals expand point group of the 0th geometry and the group named And how do you know this just works? Well, because I said so, and apparently somebody at Side Effects did too. By expanding the point group of you then get a list of all the points. Now we can loop through them. So for each int, let's just call it any point in the all points. And we're going to set point attrib 0th geometry, the prim to use of the any point, and we're going to set that to be the local new prim, and parentheses semicolon. All right, so what did we just do? Well, you remember that to have this local variable, or this global variable rather, that everybody knows is the prim that we're using. We're just simply setting that as a point attribute on all the points. So in order to update all of them, we created this giant list using the expand point group. and we set the attribute of the prim to use to be this new prim that we just created up here. So the next thing we're going to do is randomly select from our used points and use that as the place to splinter off from. So this is going to use a couple of the tricks I just showed you. So first we're going to create a list of used points, int used points array equals expand point group, zeroth geometry of the used group. Then we're going to count them. Int used points number equals length of the used points. And then we're going to do that chosen index combo. Int chosen index equals the floor of the fit of the rand of the seed from 0 to 1 to 0 to used points number. Now we're going to set point group, zeroth geometry, the current group of this new point we found, used points chosen index. Set that to 1. And then we're going to add the vertex. The zeroth geometry, our local new prim, used points chosen index. And so there you have it. We're looping through all the nearby points, seeing which ones are used and which ones are on the perimeter. If we find the endpoint, we jump to that. Otherwise, we jump to something random, unless everything's used or the perimeter, in which case we hit a dead end. We splinter off, create a new prim line, attach a used point to it, and then start the process anew. So let's just jump up here and see how much it works. All right, I knew something would go wrong. So let's just delete my little bit of Boolean trickery here and just instead chain these if statements. So let's just comment out all of this. Let's double slash, that's how you get rid of code. And so if the nearby point is not in the point number, we also want to see if it is not in the point group of used and not in the point group of the perimeter. So if not in point group zeroth geometry used nearby point, then we're going to check if it's not in point group zeroth geometry perimeter nearby point, then we are going to push the nearby point into the valid points. And put a little parenthesis here, and maybe another one here, and yeah, okay. So let's try that. And there we have it. Now, finally, our robot is happily moving along the maze, and it found its endpoint, and it's going to keep going and fill out the maze. So once again, let's just trace it along and see what's happening. On frame 1, already up here, we have created a polyline, and we have added the vertex to the start point. The start point is whatever point is closest to wherever we felt like it up there. As we progress each frame, let's go to the second frame here, it calculates up here the distance between each of these points. So then it moves that distance, and it checks in a sphere around that distance for all the nearby points. And it says, is that point in the parameter, and is it already used? If it's neither of those things, then we're going to jump to it. And it's going to continue doing that randomly until finally, let's see where it hits a dead end. It's going along there. Now, if it went to the right, or let's see, the right, it would hit the perimeter. If it went to the left, it would hit a used point. Forward and backwards are used points, so it's going to keep going a few frames until it gets to a used point with a valid destination. In this case, it picked here. So now it's splintering off. It's going along, and there we go. It found the endpoint, and it jumped there. But now when you're on the endpoint, look at this. It can't go left, because that's a perimeter. It can't go right, because that's the perimeter. It can't go forward, because there's no point. And it can't go backwards, because it's already used. Therefore, it's just going to continue on the cycle and splinter off of a used point. And this will keep going. It looks like 240 frames is enough to totally fill out this maze. There are ways we could optimize this, but this will be good enough. Now that we have this, let's go nuts, and we can go up here to this grid, and we can change the size of our maze. So let's say that we want it to be, well, whatever. I said let's go nuts. So 100 by 100. Now we'll restart the simulation, and that is a lot of points. So let's see it go. And it's clear that after 240 frames, it's not going to get very far. So just change your simulation time here to, well, actually better yet, let's go into our solver and let's change the sub-steps to, I don't know, 16. So it's going to take 16 steps every frame. Every time we go one frame, the solver is going to go 16 frames. So let's play it. Now, it's looking pretty epic. This still isn't enough frames. Let's go to, I don't know, 1,000 frames. And let's keep playing. Actually, this is still going to take forever. Let's say 64 sub-steps per frame, because I've got a powerful computer. Or, to be more precise, I'm just stealing Nate's right now. Playing along. Still haven't found that endpoint. Oh, there it is. All right, now we're just filling out all the little holes in there. All right, and after 350 frames at 64 sub-steps per frame, we have filled out this 100 by 100 grid, and we have a pretty darn epic labyrinth. There might be a problem, or maybe it's not a problem. Either way, it's pretty terrifying. This is what I like to call an ideal maze. There is one start point, there is one end point, and there is only one true path between them. If you take one wrong turn, you are doomed, which is pretty terrifying because there's a pretty big split here, just like a few steps in. If you take the wrong turn, you're doomed. So this is a little harsh. There's no way to tell whether or not you're making progress in this maze. And if, let's say this isn't a video game, and let's say you're literally walking through this maze, and it's literally 100 by 100, this could take a very, very long time to solve. In other words, you can bet your user will never solve this. So I don't think we're done here. We need to make this solvable. And I like the type of fight in a video game where you can make progress and that you're never really wasting your time. So in order to do that, we're going to need to make some extra cuts into this labyrinth. In a way, you could actually say that this will make it nastier because this will allow you to then go in circles. However, in general, this will mean that the further you go towards the end, the more progress you will make. You'll see what I mean. In order to test this properly, let's change this back from 100 by 100. And let's look at something like, I don't know. Let's go to 21 by 21. It sounds like a good number. How long does it take? Okay, that solves it pretty quickly at 64 sub-steps. So after the solver here and after this null, let's add another point wrangle. And this is kind of going to be another robot. Instead of being the robot going through with the lawnmower, though, you can think of this as one robot who every frame randomly sends out 10 lawnmowers at the same time to random points on the cornfield. The analogy may no longer make sense to you, but it makes sense to me, so that's what we're going to use. So let's add our second robot. We're actually going to do this in a detail only once, and let's call this the extra cuts. So first, let's make a slider so we can control the difficulty of our maze. Int extra cuts equals chi extra underscore cuts semicolon, and let's just get that thing there right now. All right, so there's our slider. Let's say we want 8 extra cuts. So let's start this. For int iter equals 0, iter is less than or equal to extra cuts iter plus plus. So this is a typical for loop. We're going to use this to do something extra cuts times. That's what all this means. We're initializing value to 0. As long as it is less than or equal to this number, we're going to do what's in here, and then we're going to increment it. So first of all, let's get our nice seed back here. Float seed equals, let's say the @seed modifier, which is that attribute we created up there. Now let's do the same thing. Plus, well, let's say plus iter, and then multiply by @frame. So this will give us a nice random seed every time we look. So these cuts we make are actually going to be still part of the maze, so we don't want to use the boundary points. So let's get a list of all the non-boundary points. Int non-boundary points, and that's going to be an array, equals expand point group of the non-perimeter of the zeroth geometry. And we're going to get the length of that. And let's just call this NBP length. Equals the length of the non-boundary points. Now we'll do our chosen index combo move here. Chosen index equals the floor, the fit, the rand, the seed, 0.0, 1.0, 0.0, NBP length. So this is going to choose a random non-boundary point. So int chosen point equals the non-boundary points chosen index. So now we're going to do something similar to what we did in the solver, but just one little jump. First, let's find the nearby points and see which ones are valid. Int nearby points, near points, zeroth geometry, the P attribute, and the chosen point. I want the distance between points, which we stored on the point, so we're gonna fish that out using a point attribute as well. Zeroth geometry. The distance between points, 0. You type 0 when you're just looking for a float value, not a vector value. Now we're going to create a valid points list. We're going to loop through the nearby points and see which ones are valid. For each int nearby point in the nearby points, we're going to do that same test we just did. If it's not in point group zeroth geometry perimeter nearby point, and it actually can be a used point in this case because we're trying to connect the used points, but we have to make sure that it's not the same point that we're looking at. So if nearby point is not equal to the chosen point, then it's a valid point. So push valid points the nearby point. All right, so now we know our valid points. So let's just make a cut. Int valid point length equals the length of the valid points. Just put that there. So the int chosen valid point index equals the floor of the fit of the rand of the seed from 0.0 to 1.0 to 0.0 to valid points length. And let's say that the int chosen point, or the other chosen point, equals valid points chosen valid point index. So we chose our point up there. Now our chosen other point is one of these valid points. Now to just draw the cut, int extra cut prim equals add prim, zeroth geometry, polyline. We're going to add the vertex, 0 extra cut prim, our chosen point, and then we're going to add a vertex, 0th geometry, our extra cut prim, our other chosen point. And that should do it. Add an extra parenthesis here, and there we go. So now, as we're jumping around, you see that on each frame, we draw 8 points, 8 extra cuts in random locations. Now, a couple disclaimers here. I put as little effort into this little extra function as possible, so it's really more up to 8 cuts. The cuts could land where a path already is, or there could be no valid points, I think, in which case it won't be drawn. But basically, you can have up to 8 points. This is just to add some variation here. We also added the frame, so if you don't like the look of the maze, you can just increase one frame and draw those extra cuts in different directions to get some subtle variation. And now we have a path that will sometimes go in a loop, but will have more than one route that, hypothetically, more than one route that can take you from the start to the end. Or, of course, you can just say, you can just bypass this node, in which case there will be no extra cuts and you will have what I call the ideal maze. So if all you wanted to do was pass your Sunday mornings by following a bunch of paths, you could use this and play this right now. However, this is a 3D modeling program. I'm assuming that you want to actually make a maze out of this, which means we have finally gotten started. But don't worry, the next part of this is actual art, and it doesn't take nearly that much brain power to make. So let's start working on this. All right, so now that we finally have our path, our robot has made our path by connecting the beacons, we can finally drop in the cornfield. And that's going to be a box. Actually, nah, it's just going to be a grid. Let's see, where is this grid? That's not quite right. Let's say that it's 1 by 1 as well. Let's actually make it a little smaller, like a 0.98 by 0.98. And this is going to be a thing that we cut out of. And we're going to cut this path out of that grid. First, let's transform this whole thing. Bring it back to the center. Let's say negative 0.5, negative 0.5. All right, so this grid is going to be the cornfield that we cut out of. Now we need to really determine how big the lawnmower is. So we're going to sweep a grid along this to get a sort of blocky path. So let's create another grid. And let's say that it's a 2 by 2 grid. And it's very tiny, 0.02 by 0.02. And we're going to, the other thing is, this is just going to kind of work if we put it in the XY plane. Now we're going to sweep it along this path. We're going to angle fix it, which will make our diagonals a little longer, so it'll just look nice and blocky. And then we're going to skin output, skin unclosed. And there you go. So now we have our sort of block. Or, you know, maybe this is all you need for your game, because you could actually kind of walk in there, or, you know, maybe not. I don't know. You can work with it. So now we're going to cut that out of this. In order to do that, we're going to have to do a polyfill here, or a polycap. All right, so now we want to cut this here out of this here. So let's see. First thing I'm saying is that this is inside out, so we're going to reverse it. And that looks about right. Now we're going to Boolean subtract, let's see, this solid from that surface. And Boolean subtract. All right, let's see. Is that going to work? That works. Okay. Now what we have here is a two-dimensional maze with all the walls. And let's see here. If all we need to do now is a poly extrude. Let's look at that and give it some distance. And there you go. You now have a labyrinth. You can make the walls as short or tall as you want. You know, down at the little hedge maze, or, you know, full-on Maze Runner novel there with infinite tall walls. And let's see. We might want to expose a couple extra parameters here. This right here, the square that we're sweeping along, determines the width of the path, or otherwise the thinness of the wall. So if we said 0.03, 0.03, we'll get skinnier walls. I think I like that better. Maybe even more. 0.04 by 0.04? Yeah. As you see, it's not really perfect here. We should actually probably be sweeping a cube instead of a square. But whatever, this gets the job done. And you can use this general mentality to make this however you want. All right, so there you have it. We sent our robot through through a giant grid of beacons. It chose its random path, and it found a path from the start to the end, and then filled up the entire maze with paths. Then, for good measure, we added some extra cuts in the end to make this maze more solvable and more tolerable. And now we have a maze with that of arbitrary size and of arbitrary shape. And most of this was just finding the path, and then creating the walls that would have such a path turned out to be quite easy. And as you see, this is really just the very bare basics of it. You can do whatever you want to make this any shape you want. What I like to do in order to make my low poly hedge maze was I did a remesh, made a very tiny target edge length, and then added a mountain sop of a very tiny height. And now you can imagine just sort of walking around in there. And of course you could always just go in there and hand tweak it if you want. But the glory of this is that this will work for anything. For example, if we wanted to change the number of rows and columns in here, it's just simply a matter of tweaking a couple variables, and then of course of re-simulating the maze, and there you go. So, I hope you found this useful. My goal here was to bridge the gap between knowing what Vex is and knowing how to create something truly amazing in Vex that nobody's ever seen before. And obviously, if you just followed along with this tutorial perfectly, you will not have done that, because I personally have already seen this labyrinth before. But that's not really what the point of this tutorial was. The point of this was so that you know how to take a basic concept, like creating a maze, figure out an algorithm, which in this case was a robot going through a cornfield with a lawnmower, and then figuring out bit by bit how to turn that algorithm into code. Now, you didn't really see that whole process because that took me, honestly, a couple of weeks. But suffice to say that it's possible if you dream hard enough. This is just one of many tutorials that we hope to do in this series. Put that in your pipeline. And I hope you subscribe to our channel so that you can see the next one. And until then,